Now that you've had an overview of what the work and energy chapter is going to contain, we're going to start simple by connecting this unit to our previous topic of dynamics with the idea of work done by a constant force. Remember that a constant force means that force doesn't change in magnitude or direction. So that means that it has to be the same force pointing in the same direction the entire time, and then work can be done. I'm also going to have you recall the definition of work. Work in physics is the result of a force acting on an object over a distance displaced. Alright, so that means that an object must have a force. That force must be acting while the object is displaced, and more specifically, that force must act in the direction of the displacement. So when work is done by a constant force, both constant in magnitude and direction, the work can be defined as the magnitude of displacement, or how much it's displaced, times the force that's acting in that direction, the force that is parallel to that displacement. We can write that symbolically as work equals the parallel component of the force times the displacement that it underwent. It's very important to note that in order for work to be done, the force that was applied has to have some component or some piece that acts in the same direction as its displacement. A force that is not at all in the direction of displacement will not do work to that object. Likewise, if you apply a very large force but only a very small component of it works in one direction, say for example you are displacing something in this direction, and then you apply an enormous force in this direction, well, take a look. Only a very small component of that force, because force is a vector and can be broken down into components, only this component does any work. So no matter how big your force, if only a small amount is headed in the direction of the displacement, then that's the only part of it that's doing work. All of that other force, well, it was either wasted or it was serving a different purpose than to do work on that object. So you're going to notice this symbol, which is the F with the two lines, and that is a component of force that's parallel to the displacement. So you will be breaking forces down into components. Let's take a look here. Well, if we have a situation like this, where an object, this is our spherical cow, and you're pushing this cow, and you're pushing it, you've got its hands up underneath its haunches, and you're pushing kind of up and forward. So that means that your force vector is up and forward at this angle theta. And we're going to be looking at what amount of this force is in the same direction as the displacement that the cow is going. Because you're not accelerating the cow upward into the air. If we were going to look at this, we would also have, right, the mg of the cow and the fn of the cow, and we could do our x and y components. But you can see that the only force acting in the x direction, the force of u, right, that component is in the x direction. So what is that component for this force? Well, it's this force, and it's separated from the displacement by this angle. So that means that this component of the force right here would actually be force times the cosine of theta. Right? And in that case, we're talking about F is the force being analyzed. Theta is the angle of separation between the force and the displacement. So that angle can actually be anywhere from 0 degree to 90 degree to 180 degree if the force is in the opposite direction, to 180 degree if the force is down, to 360, which would be the equivalent of 0. Why would you use 360? And D is the displacement, distance. And even though work is a scalar quantity, remember that that displacement is still a vector. This equation right here will always be true. All right? For any situation, the parallel force will always equal F cosine theta. So that means that if work equals the parallel force times distance, then work equals F cosine theta times d. And that is our work equation. It just happens that when you see it, oftentimes it's just rearranged so that work equals force times distance times cosine theta. And that's done as just a convention, because order of operations says you may multiply those in any order and the product will be the same. So there's our work equation. It's going to consider any force that's applied, and as long as you are taking into account the angle of separation between the force and the displacement, you will always be calculating the work of the force that you're calculating for. So that means you're looking at forces. When you do problems like this, you're still going to want to draw and make free body diagrams. Draw the situation, make a free body diagram of whatever it is you decide that you're studying. That's still going to be true. In fact, in physics, I have a saying, if you can draw a free body diagram, you probably should be drawing a free body diagram. So, if F cosine theta will always equal the parallel force, that means that we have to draw a free body diagram where we can figure out, well, there's your force. Now here's the displacement. So that means, oh, look, there's your angle. You're going to have to determine the angle of separation, because without that picture, without a free body diagram and a description of what's going on, how would you be able to figure out what your angle of separation is? Please make sure that you know, even though force is a vector quantity, even though displacement is a vector quantity, the work that you calculate as a product of these values is only magnitude. There is no direction. Work is scalar, which means that if you have a positive value for work, it does not mean in the positive direction. And if you have a negative value done by work, it does not mean that it was a negative direction. The positive and the negative for work actually mean the work was added to the system or the work was removed from the system. If work was done on an object, well, then that work was positive and that work was gained by the system. The work was done to the system gained the benefit of that work. Negative work is work done by a system. In that situation, the system did work, therefore that work was at a loss from the system. So the positive and the negative values now have a result of gain or loss. Just like mass is a scalar quantity, so if you had a positive mass, that means your mass changed in the positive direction. You got more mass. If you had a negative mass, then that means that that mass was removed from the situation. Same type of concept for work, but remember, work is some sort of numerical mathematical quantity that is a little bit abstract, can't be seen, can't be held. When the force and the displacement are in the same direction, you can still use this equation, work equals force times distance times cosine of theta. But if the force and the displacement are in the same direction, well, then the angle of separation is going to be 0. Well, guess what? Has anybody ever really thought about what the cosine of 0 degrees is? That's right, it's 1. So work and force and displacement in the same direction would be force times distance times 1. So here we'll consider Benny is pushing a box. He is applying a directly horizontal force, and it's displacing the box D. we're only going to be considering Benny's force. There may or may not be friction. We don't know. We don't really care, because all we're curious about is if Benny applies this force over this distance, we can use the equation work equals force times displacement times the cosine of theta. Here, the force and the distance are happening in the exact same direction, so it's going to be a force of 30 newtons, a displacement of 50 meters, so work is going to equal 30 newtons times 50 meters times the cosine of 0, which is 1. 30 times 50 is going to be 1,500 Newton meters. And those are the units. The unit is actually going to be something that you can write in shorthand, because 1 Newton meter, as is defined by the SI system, is equal to 1 joule, which is given by the abbreviation J. So that means the units of work are actually joules. Joules are equivalent to Newton meters by a 1-to-1 ratio. So here we can take a look at a situation where we're considering amounts of work done. All right, imagine the same work, the same force Benny is going to apply. So this force and this force are equivalent. We're also going to establish the displacement is in this direction. So the angle that separates the displacement and the force are equal in both situations. So if we consider this, even though one force is up and one force is down, the parallel force is still going to be F cosine theta. And if the angle of separation is the same for both of these, then F cosine theta will be the same for both of them. So even though Benny could push in one situation and pull in the other situation, the work that Benny does is going to be equal in both of those situations. So if Benny's force is the only force occurring, then it will be an equal amount of work whether he pushes or pulls the crate, as long as the force and the angle are equal and he displaces it the same amount in both situations. Now we know in real world situations, this crate of puppies that Benny happens to be pushing probably is experiencing some sort of friction. And we know that friction is equal to coefficient times normal force. And if we consider this a level surface, then we know that normal force is going to be equal to the weight of the object. And now we have to consider our net force in the y direction with a push or a pull is going to change this value, because if it's at an angle, then some component of each of these forces is also in the y direction. So that means that, well, if he's pulling, then it would be normal force and the pull force are in the same direction, and that's going to be minus the weight, and that will give us a value of 0. So in this case, the normal force is going to be the weight less the force that it got pulled with in the y direction. In the push situation, while Benny is pushing, so that means that the normal force is actually opposing both the push y force component and the gravity component, so that there's no acceleration. In this situation, the normal force is going to be equal to the sum of the weight and the force of being pushed in the y direction. So that means that we could change the force of friction for this crate of puppies by determining whether Benny is going to push or pull. If he pushes, he's going to increase the force of friction because he's going to increase the normal force. If he pulls, he's going to decrease the force of friction. Therefore, he's going to decrease the normal force, decrease the force of friction. Why is that important? Well, friction can do work also. And if the force of friction is bigger over the same distance, then friction will do more work against Benny. But if the force of friction is smaller and acts over the same distance, well, then the force of friction is going to do less work. Now that could potentially have an effect on Benny's perceived effort. But as long as the force and the angle are the same, it will not change how much work Benny does to the box. So there are situations that can occur where a force can be applied to an object but no work is done. Take, for example, a look at this situation where Benny is giving you a love lock hold. In this situation, you are pushing against Benny in an attempt to free yourself. You push Benny with all of your might, and your force is exerted in the horizontal direction. But Benny is so much bigger and stronger than you, therefore no matter how hard you push, Benny doesn't go anywhere, therefore his displacement is 0. And work equals the parallel force times the force times the distance times the angle of separation between the two. If the displacement is 0, then the work is also going to be 0. And that's true regardless of the magnitude of force. It does not matter how much force you apply. If the object is not displaced, then no work has been done by that force. Holding a heavy bag of scorpions is another example. So imagine here's Scorpion Delivery Benny. He's holding a heavy bag of scorpions. So he's holding it, and right now he's perfectly still. He's at rest. Alright, if Benny is at rest, well then let's consider what is occurring. Here, there's the weight of the bag pulling down, so Benny's arms are getting tired, and here is the force that Benny is applying to hold the bag up so that it can remain at rest. The force that Benny is applying is equal to the weight of the bag, and the net force is 0, and this object is at rest. At rest, the displacement equals 0. Therefore, the work is going to be equal to the work that Benny is doing is going to be equal to the force that he applies times the displacement, which is 0, times the cosine of their separation. And we don't know, since there is no distance, then we don't know what that angle is, but it doesn't matter because displacement is 0, therefore work is 0. So no matter how heavy that bag is, Benny is doing no work to the bag because the bag is not being displaced. So now what if Benny is actually transporting the bag? He's walking in this direction, so the bag is going to be displaced because he's moving it in that direction. For simplicity, we're going to say that he covers this distance with uniform motion, which means that his velocity is equal to a constant and his acceleration equals 0. Now in this situation there is a displacement, and work equals force times distance times the cosine of separation between the two. Now the displacement is forward, and the force that Benny is applying to hold the bag up and walk in a straight line in a constant motion is up. So those actually happen to be separated by a 90-degree angle. And what's the cosine of a 90-degree angle? Well, of course, the cosine of a 90-degree angle is 0. So that means in this case, the work would equal the force that Benny was applying to the bag times the displacement that he moved the bag. That's a quantity, but then we're going to multiply it by the cosine of 90, which is 0. So therefore, even though Benny was holding the bag up, he was applying a force. That force did no work on the object because that force was not in the direction that the object was displaced. So even if you walk at a constant velocity, if the angle is 90 degree, or likewise 270 degree, so that would be relative to the distance or the displacement. That would be a force directly up would be 90 degree. A force directly down would be 270 degree. You could also use negative 90 degree, but 270 degree would be that. In either of those cases, the cosine of 90 and the cosine of 270 both equal 0, and therefore no work is done, because no component of force was in the same direction as the displacement. So Benny carrying that grocery bag at a constant velocity meant that he did no work on the grocery bag. There was no net work done. Realistically, Benny did do some work, and the work that Benny did was in starting and stopping. Because starting and stopping, moving a bag over that displacement, there is some acceleration. To go from rest to motion, there's acceleration. And that acceleration requires the net force in that direction. So that means that there would be some parallel force, and that means that some work would be done in order to accelerate and decelerate that bag in that direction. However, as long as he's traveling with uniform motion, the net work done is 0 because the force has no component in the direction of the displacement. So I already mentioned a little bit about when you calculate work, you need to specify if the work is done by the object or if the work is done on the object. Work can be done by an object. For example, let's pretend that the object is this bulldozer. The bulldozer is doing work, and this is going to do work or it's going to, the work is being done by the dozer. Alright, so here work is being done by our object. Our object is the bulldozer. When work is being done by the dozer, that means that work is leaving the dozer and going somewhere else. Work can be done on an object. If our object is the boulder, well, work is done on the boulder. So that means we're changing the boulder motion and displacement with the dozer. The work is done by the dozer. The work is done on the boulder. So work can be done by an object and it can be done on an object. When you calculate your work, you must specify if you're calculating work done by one particular force or by the sum of all forces also. So we not only have to be very specific in saying this object is doing this work or this object is having this work done to it. And that's going to make a lot more sense even when we talk about energy. So we have to be sure if we know, is the work getting done to the object or is the work getting done by the object? And also we have to be specific. Is the work getting done, are we focusing on one force and the work that one force is doing, or are we looking at the net force on an object? And of course this means free body diagrams. So you guys know that there's a difference between one force and the sum of all forces, or the net force. And that means that since we know our equation is the parallel force to the displacement is going to equal work, right? If it's that one force, then that would give us the work done by that force. If it's done by a net force, then that net force would give us the net work done on the whole object. So this equation would give us the work that one force did, the force that we were focusing on. This equation would give us the net work that all of the forces, the sum of all of the forces, did on the object. And there's going to be a difference between these. If you are solving for net work, you can solve using this equation. If you're solving for one particular force, though, you must use this equation. So let's look at an example. We're going to take a look at the amount of work done on a crate of scorpions. And to do this example problem, we need to know that the mass of the crate is 50 kilograms. We also need to know that the resistive force on the crate is 50 newtons. We may need to calculate the normal force and the force of weight. And this force, this crate is having an object pull on it, so a force is being applied to it at a 37-degree angle with a value of 100 newtons. And we want to calculate the work done by each individual force, and we also want to calculate the net work done on the object. So the first thing that we're going to want to do is we're going to want to draw a free body diagram. According to this free body diagram, we have FP, which is 100 newtons, and that 100 newtons is getting separated by an angle of 37 degrees from the direction that the crate is being moved. That crate is being moved 40 meters. That crate is also experiencing the force of friction. If we want to set an angle compared to the direction of displacement, that would be a 180-degree angle away from the displacement. This crate is also, of course, experiencing the normal force, and this crate is also, of course, experiencing mg. Now, if we were going to calculate the work done by each force, then we would use the equation that work is going to equal FD cosine theta for each force. So let's start with the force of friction. The work done by friction is going to be the force of friction times the displacement of the crate times the angle of separation of those two objects. So that means that the work done by friction is going to be 50 newtons times 40 meters times the cosine of, we decided the separation between the displacement and the friction is 180. Cosine of 180 is -1. And so we're going to have -1 times 50 newtons times 40 meters. So the work done by friction is a -2,000 joules, 2,000 newton meters. We haven't calculated the weight or the normal force of this object, and we can do that because we could, in this free body diagram, we know what mg is going to be equal to. The net force in the y direction is the normal force, the y component of the pull, and the weight. So we could figure out what the normal force is. But let's take a look at something. What's the angle of separation between the displacement and the normal force? Well, the work done by the normal force is going to be the normal force times the displacement times the cosine of angle of separation, which is 90 degrees. Cosine of 90 degrees equals 0. Therefore, it doesn't matter what the normal force is, because that normal force times 40 meters times 0 means that the work done by the normal force equals 0. So I just saved you from having to calculate the actual numerical value of normal force. Already, work is working out for you. Likewise, I could say that the weight of the object is at a -90 degree or 270 degree from the displacement of the object. So that means that the work done by gravity is going to be mg times displacement times the cosine of 270. The cosine of 270 is also 0. Therefore, the work done by the weight of the object is 0. So we've now solved for the work done by friction, the work done by normal force, the work done by the weight of the object. So now all that's left is to figure out the work done by the pulling guy, which is going to be F, the pulling guy, times displacement of the object, times the cosine, the angle of separation, which is 37 degrees. So that's going to be 100 newtons times 40 meters times the cosine of 37, which should give us 3,195 joules. So we've found the work done by each force. Now we need to figure out the net work. Alright, so the net work can be solved two ways. One way that we could solve it is, well, the net work is going to be the work of the friction plus the work of the normal force plus the work of gravity plus the work of the pull. So we could add those up. Negative 2,000 plus 0 plus 0 plus 3,195 equals 1195, which we need to round by significant figures. There's only two significant figures in any of these numbers, so that actually rounds to 1,200 joules. And that would be the net work. The other way we could do this is we could calculate the net work by using the net force times the displacement times the cosine of theta. And in that case, we would just take the force of the pull and the force of the friction, and so it would be F pull cosine theta minus F friction, and that would give us the net force. The net force would then be 37 cosine times 100 would be 79.8 newtons, and we're going to minus the force of friction, which was 50 newtons. So the net force would be 29.86 newtons, and that was applied, and that's a positive value, that was applied over 40 meters. And guess what? If net work equals the net force times displacement times the cosine of separation, then we still get the value 1195 joules, which rounds to 1,200 joules. So it doesn't matter which way you solve, you get the same answer whether you use the net work equation where you add together the sum of all of the individual works, or if you use the net force and the angle of separation between the net force and the object, which is pretty neat because you can kind of do whichever one you decide you like the best. One of the things that you may have noticed is that friction does negative work. We had a negative 2,000 joules for that example. Well, friction does negative work because it opposes the motion. All opposing forces do negative work. So if we take a look at a picture, right, where we have displacement in this direction and an opposing force, the angle there is always going to be a 180 degree angle. And the cosine of 180 degrees is always going to be -1. So this is always going to give us negative work. opposing forces, what does that mean? It doesn't mean that the object is working in the negative direction. What it means is that opposing forces try to slow objects down. That's what their work does. Their work removes from the system. In this case, it's removing the motion. And we have a vague understanding that the motion is related to the object's ability to do work. So an opposing force takes work away from an object, takes away an object's ability to do work. An opposing force actually would slow an object down as long as there were no forces working against the opposing force. In other words, if the net force were only opposing forces, only forces working at a 180-degree angle, then that object would slow down, and that would be negative work. The object would lose motion, which means it would lose work or lose its ability to do work. Negative work happens when objects slow down. When an object slows down, it loses work and it loses the ability to do work. When an object has positive work happening, that means that the object is speeding up or it's gaining work. It has more ability to do work. And you're going to see that there's this relationship between the work and the motion of an object that's going to become incredibly important in our very next lecture. So let's take a look at some applications. You decided to do some work. Ha ha ha. So remember, when you decide to solve problems like this, even though we're moving away from the units that focus specifically on dynamics, so even though we're moving away from forces and even though we're moving away from circular motion, you're still going to be drawing free body diagrams, and in your free body diagrams you're still going to want to be very certain to choose an X and a Y axis, because we want very much to still know what direction the forces and the displacement are, because those angles are going to be important for our scalar quantity of work. A tip is always choose your x-axis or your y-axis in the direction of the displacement. It will give you much simpler answers if you make your displacement along one of the axes. After you've drawn your free body diagram and set your axes, you're going to do what you will always do. You're going to apply Newton's laws to calculate all of the forces. So you're going to find the net force in each direction and then use those equations to find the value of each individual force. Once you have the value of each individual force, you will use that value to find the work done by each of those forces using the equation work equals force times displacement times the cosine of the angle that separates them. If you've found the work done by each force, then you can find the net work. You can find the net work, or the sum of all the work, either using the equation of adding all of the individual works together, or you could use the equation net work equals net force times the displacement times the cosine that separates the net force and the displacement. If you use this equation, make sure that your theta here is your theta for your net force, which means if you found net force and there is an angle from an axis, you need to make sure that you account for the displacement between that force and the object's direction of travel. Now, if there is an overall net force, it should be in the direction that the object is traveling, but it won't always be that way, because remember, force determines acceleration, and a net force could cause an object to be slowing down. In that case, the angle would be 180 degrees, or it could be causing an object to change directions. In that case, it would be another angle. So make sure that you're being very aware of the angle of your net force. Here we're going to take a look at an example, and this is a really neat example because this also begins to give us the beginning workings of the relationship between work and the potential to do work, or potential energy. So we're going to be looking at the work that Benny does on a backpack full of scorpions. So here Benny is going to be hiking up a hill. And that hill, we're going to set our angle from here so that we can be investigating that angle. But Benny is going to take his backpack and he is going to travel a distance up to the top of the hill, and this hill has an angle of theta. So that means that this one is going to be 90 minus theta. Or is it 180 minus theta? I always forget. It's 180 minus 90 minus theta, 90 minus theta, something like that. So, a few variables that we can know is the mass of the backpack is 15 kilograms. The height of the hill here is 10 meters. And we're going to assume that Benny travels from the bottom to the top with a smooth, constant velocity. So we're assuming uniform motion, or we're assuming that acceleration equals 0. So that means that the net force in all directions is 0. So we're going to find the work that Benny did, the work that gravity did, and the net work done on the backpack, which means that we need to draw a free body diagram. So far you're probably thinking, this seems absolutely no different, Miss B, from what we've been doing this whole time. And in that sense, you're kind of correct. Okay, so the object that we're interested in is the backpack. So here it is. Here's the backpack. Now let's consider what forces are acting on the backpack. You've got the weight of the backpack downward, and you've got the force that Benny is applying to the backpack upward. And we know that those are the only two forces that are acting. We're going to set, in this one, we're just going to say that up is y, forward is x. And we're going to say that the net force in this situation is the force of Benny minus the weight of the backpack equals 0. There's no net force. Benny is moving with uniform motion. He is not accelerating upward or downward because he did not fall off of this cliff. So now, let's consider the relationship between Benny's force and the relationship between the displacement. Now here we need to be very specific, because in order for us to find the work that Benny did, we need to know the force that Benny did compared to the displacement. So we have this free body diagram, right, where Benny's force is up and gravity is down, but the displacement is along a hill here, and that hill, if I consider, had an angle theta right here. So if I'm going to analyze this, then that means that through similar triangles, right, this is 180 minus theta, this is theta by similar triangle. This is 180 minus theta, and this is theta. So we've found all of our thetas in this free body diagram. And remember that the reason that this line is here, this is the hill, this is the displacement. So that makes this theta right here the angle of separation between Benny's force and the displacement of the backpack up the hill. So Benny's force parallel equals the force of Benny times cosine of theta, and work equal the work that Benny did equals the force of Benny times the displacement of the backpack times the cosine of theta. And now you might be thinking, oh shoot, Miss B, because we don't know what the angle of separation is, and we don't know how high or how long it took Benny to climb up that hill. All we know is that that hill was 10 meters high. Well, now let's think about it. In this triangle here, here's the height, here's the displacement, here's an angle. What's the relationship between the displacement and the height and that angle? Well, if I look at it, that is the adjacent. So that means that the cosine of that angle equals adjacent over hypotenuse, and the hypotenuse is d. I know the height, so I'm going to solve it in terms of height, and I'm going to say that the height, which is a value I could plug in, is equal to d cosine theta. So that means d cosine theta equals 10.0 meters. take a look here. D cosine theta is this value right here. So I'm going to replace that with the work that Benny did is equal to the force that Benny applied times the height. Now I need to think. In my free body diagram, I said that the force that Benny applied and the weight of the backpack are equal and opposite. So that means that FB equals mg. So that means that the work that Benny did equals the weight of the backpack times the height, or 15 kilograms times 9.8 meters per second squared times 10 meters, or the work that Benny did is equal to 1,470 joules. So we've got that. The work Benny did is 1,470 joules. Now, the angle of separation between the displacement and gravity here is also going to be needed. And so if we're going to find the work that gravity did, then it would be the force of gravity times displacement times the cosine of theta. And in this case, the cosine of theta is actually 180 minus theta. So if I plug in, I'm going to plug in mg for gravity. So the work of gravity equals mg times d times the cosine of 180 minus theta. And you know by that principle that the 180 minus theta, this is a trigonometric concept, but cosine of 180 minus an angle is equal to negative cosine of the original angle. And so if you didn't know that trigonometric proof, remember that you have these trigonometric proofs able to look up, or you could just check it out concept-wise. This is also going to be true. So that means that the work done by gravity is going to be equal to the negative mg times d cosine theta, and d cosine theta still equals h, so that means the work done by gravity is equal to a negative 1,470 joules. So the work of gravity is negative 1,470 joules. And now the net work, I'm going to just the work of Benny plus the work of gravity, because I don't really feel like finding, oh wait, the net force is 0. So net force is 0 times the displacement, which is d cosine theta, which is h. So no matter which way I do it, I could say positive 1,470 joules minus 1,470 joules equals 0. Or I could say that the net work is equal to the net force times d. And in that case, the net force equals 0. So it would be 0 d cosine theta times d cosine theta, which we solved for was height. So 0 times 10 meters also equals 0. So no matter which way we solve for work, whether we solve for it by adding up the individual work of the individual forces, or whether we calculate the net work done by the net forces, in both cases we get that the net work is 0, which is pretty dang neat. So I said I was going to start simple, and we did by looking at the equation that we could use to solve for the work done by a constant force. So you might ask the question, why can't we use the equation work equals force times distance times cosine theta in order to solve for non-constant forces? In other words, work done by varying forces, forces that change as the displacement changes. There's a lot of forces that change in either their magnitude or their direction during a process. Take, for example, this situation where a rocket is moving with a displacement away from Earth. Well, the force that this rocket was experiencing is the gravitational force, and gravitational force equals GMM over r squared. Well, we know that as this object travels this distance, the radius is going to get larger, and our force of gravity is inversely proportional to the radius squared, which means that the further away this rocket gets, the weaker the force is going to become. Graphically, that means that we'd be looking at it, and we'd say, here's the force of gravity that the rocket is experiencing, here's the displacement or radius from the center of the Earth, and it's going to be inverse, so it's going to be right as the rocket moves further and further away from Earth, the force that it experiences is becoming less and less. Bummer. So that means that that's a varying force. Likewise, when you wind up a spring, if you have a spring and you push it in a little bit, it doesn't take very much force. However, the more you push that spring in, the more force it then will apply. So that means the relationship between the force in a spring and the displacement gets greater, right? Here's the force of the spring, and here's the displacement as you push it in or stretch it out, right? That force is going to increase. So that means that this is a varying force. It changes as the displacement changes. And likewise, Benny carrying his crate of scorpions up an uneven hill, here the force is going to change depending on where he is on the hill. So again, this force of Benny, is going to be a little bit all over the place as he travels up the hill. In all of these situations, the force isn't constant, and so you cannot just plug one value into the equation, work equals force times displacement times cosine theta. But you can use a graph to solve. And here is where calculus plays an important role in physics. And we're just going to take a look at the role, and we're going to take a look at what you could do, whether you're in calculus or not. You can use a graph to solve for the work done. And this is a lot like using a position versus time graph, right? If you did a position versus time, dt, and you found the slope, you might be able to find meters per second or velocity. If you did a velocity versus time graph and you had a value, if you found the area under a curve, right, that would be meters per second, and area under the curve would be meters per second times second, you would find the displacement. So here, what we're going to do is we're going to take a look for a varying force, a force that changes as you change your displacement. If you found the area underneath that curve, that would be, area is base times height, or length times width. So here it would be force times distance, which would be newtons meters. So that would be joules. Hey, that's work. So work equals the area under a curve. And if we were going to do this algebraically, what we'd have to do is we'd have to figure out, by breaking it down into smaller chunks, we'd get the approximate area under the curve, right? We'd find the area of each of these even pieces. All right, and when we found this area here, area approximates work. So we can do that by breaking each distance into a smaller distance, and that gives us a more and more accurate area under the curve. Well, you know, in calculus, as this distance becomes small, as the limit of the distance approaches 0, well, now we're talking about an integral, and if you find an area under the curve, which is what you do in calculus, then you've found the force times the distance for a varying force. You've been able to calculate what's happening when the force is changing and the work that's caused by a changing force. The worst that you would have to do in this class is you would have to take a look at it and you would have to find some average area under a curve by breaking it down numerically. You would not have to actually apply calculus to find area under a curve for a smooth curve, but if you wanted to, be my guest. In fact, they do not disallow that on the AP test. Your problems, which are to be brought into class on Friday, are problems 2, 4, and 8. Problems 2 and 4 are both level 1 problems. You're going to be calculating work using force times displacement times the cosine of the angle that separates them. This is your equation. Now, whether this F right here is for an individual force or a net force is up to you to determine by reading and interpreting the problem. Problem number 8 is a level 2 problem. However, you're still using just this equation, and you're going to use it for individual forces and for the net forces, for individual work and for the net work. The real trick here is draw a very good free body diagram and find each of the individual forces, just as we did in our example problem 6-2. I expect all of the problems at minimum set up in class.